Dear students, after studying this module, you shall be able to understand the connection between molecular symmetry and chirality. You should also be able to differentiate between chiral and prochiral molecules. You shall be able to know the difference between homotopic and heterotopic ligands and phases. You shall be able to identify the prochirality in molecules along with the identification of different types of stereotopic ligands and phases in various molecules. So let us introduce the topic of molecular symmetry and chirality to you. A molecule or an object can have only one mirror image. If the image is superimposable on the original molecule, the molecule is said to be achiral. On the other hand, students, as you know, if it is not superimposable on the original molecule, the molecule and its mirror image are said to form two distinct species called enantiomers, giving rise to a type of stereoisomerism known as enantiomerism. Such molecules are chiral and the two enantiomers are said to differ in their sense of chirality or handedness in the same way as the right hand differs from the left hand. Three terms have almost been used interchangeably to describe molecules which show enantiomerism. They are asymmetric, dissymmetric and chiral. The term chiral is synonymous with dissymmetric, as is given by Eliel and Wieland in 1962, although the former is now getting wider currency. The term asymmetric or asymmetry has a slightly different connotation in the sense that symmetry elements are absent except for the trivial C1 axis. The diagram clarifies the situation described. So you can see the molecules can either be chiral or achiral or chiral or dissymmetric. So dissymmetric should be having the C1, Cn or Dn elements of symmetry. If it does not have any Cn type of symmetry, it is asymmetric having the C1 type of symmetry. So after having described this table and connection between molecular symmetry and chirality, I would like to now go on to prochirality. Molecules which display chirality are called chiral. For example, S plus lactic acid is chiral. Chirality, as explained and depicted above, is associated with this type of molecules, is known as center of chirality, and chiral center at C2 carbon exists. Some other type of chirality types is also present in molecules which does not have any chiral center, but they show chirality due to dissymmetrization of axes and planes. Now you can see here we have described the chiral and prochiral molecules. So prochiral is one molecule where by change of one atom or a group you will get a chiral entity. In the molecules like propionic acid, replacement of HA, as I said just now, or HB by the OH gives rise to S plus lactic acid or R minus lactic acid. The protons HA and HB of the propionic acid, they have the protons in different place, hence they are known as heterotopic. The molecule 2 shown here is prochiral, which means that this can be converted to a chiral compound 1 by replacing its ligands either HA or HB by the different ligands OH. The carbon C2 is called as prochiral center as shown in the figure. The term chirality in stereoisomerism should be similarly be replaced by the term prochirality in prostereoisomerism, which would mean that if two homomorphic ligands at a prochiral center or axis or even plane be made different, a chiral center or an axis or a plane would thus result. Just as a stereogenic center may not be necessarily chiral, a proto-stereogenic center or a pro-stereogenic center may not necessarily be a prochiral center. That is, a center may be prostereogenic without being prochiral, as it is shown here in the figure. Taking the example of propionic acid as discussed above. Substitution is one of the common ways to interconvert the organic molecules. The lactic acid in principle can be synthesized by the addition of methyl magnesium bromide to carbonyl of the glyoxylic acid, which may be necessary to protect the acid group as an ester. Now we should note here that the attack of the Grignard reagent on the front face of the carbonyl gives S-lactic acid and the attack on the rear face gives R-lactic acid. Thus, the carbonyl group in the glyoxylic acid also is prochiral and present as two heterotopic faces. Now you can see that glyoxylic acid is shown here to you, and by the attack on different faces, either the front attack or the rear attack, gives different lactic acid in terms of chirality. So you can see here the attack is shown here in this figure. Now let us see this topic from the historical point of view. From the chemical point of view, the most significant aspect of the present topic lies in the possibility of differentiating the heterotopic ligands attached to elements of prostereoisomerism or heterotopic faces of a prostereogenic double bond. The concept of heterotopic ligands and their recognition in suitable instances by NMR spectroscopy was first historically presented in a pioneering article by Mislow and Raban in this Stereochemistry 1 in 1967, on which much of the subsequent discussion is based. Historically, students, the first significant observation involving this was the decarboxylation of methyl ethyl malonic acid, shown here as molecule number 4, to methyl alpha methyl butyric acid 5 in the presence of brucine numbered as 6 as a chiral source. The C2 carbon in alpha methyl butyric acid is a chiral center. The C2 carbon in the malonic ester or acid is a precursor, is a prochiral center. The product as shown is optically active. Indeed, this is one of the first recorded asymmetric synthesis. Clearly, the superficial impression that the two carboxylic groups of the starting malonic acid are equivalent in principle is distinguished in the presence of a chiral catalyst brucine. Otherwise, it would not have been possible. Now you can see here in this figure whatever I have explained. Now let us come, after studying the historical aspect, let us come down to the homotopic and heterotopic ligands and faces. First in this I would like to discuss topicity of ligands and faces. A ligand cannot itself be called homotopic or heterotopic. In order to use this terminology, a comparison with the other homomorphic ligand or ligands present either in the same molecule by internal comparison or in a different molecule by external comparison is necessary. Now what are homotopic ligands and faces? Some of the apparently identical ligands are not equivalent towards enzymes or in their NMR signals. How will we decide whether the nuclei, that is a ligand, are equivalent? There are two criteria for this. First is the substitution criterion and the second is the symmetry criterion. Similarly, addition and symmetry criterion serve to test the equivalency of faces also. Now let us first study the substitution and addition criterion. Two homomorphic ligands, that is homos means same and morph means form, that is ligands of the same form, are homotopic if the replacement of first one and then the other by different ligand leads to the same structure. Two hydrogen atoms of the methylene bromide, that is structure number 7, are homotopic because replacement of either by chlorine gives the same dibromochloromethyl. As you can see that the two hydrogen atoms of the methylene bromide, molecule number 7, are homotopic because replacement of either by chlorine gives the same product, that is dibromochloromethane. You can see here the homotopic ligands in methylene bromide as an example. The three hydrogen atoms in acetic acid as shown here are homotopic because replacement of any one of them by fluorine gives the same fluoroacetic acid. Now this is shown to you here in the figure. Methine hydrogen atoms in R-tartaric acid are homotopic because replacement of either one of them by deuterium gives the same 2R, 3R tartaric acid, D acid. Now you can see here in this figure the homotopic ligands in tartaric acid as described. Now we shall study the homotopic phases. Two phases of molecules, usually but not invariably phases of double bond, are homotopic when addition of the same reagent to either phase gives the same addition product. For example, reduction of acetone 13 as shown here with NaBH4, that is sodium borohydride, will give the same reduced product 2-propanol by the attack of front phase and the rear phase. Now you can see here the homotopic phases of acetone and how they work in this reaction. Two phases of ethylene are homotopic and the attack of bromine on either of the phase gives 1,2-dibromoethane as a product as shown to you here. You can see the homotopic phases of ethylene clearly. The phases of carbonyl group in acetone and the phases of alkene in ethylene are homotopic because by the addition of a reagent on both of the phases, you get the same kind of products. Now let us discuss the second criteria, which is the symmetry criterion. Other criteria to find out the homotopic ligands and phases are symmetry criteria. Students, if you know that ligands are homotopic if they can interchange places through the operation of C-N symmetry axis. The bromine atoms in the methylene bromide having a symmetry point group of C2V are homotopic because they exchange places through 180-degree turn around C2 axis. Now you can see here the rotation through C2 axis of methylene bromide. It is important to note that presence of a symmetry axis in the molecule does not guarantee that the homomorphic ligands will be homotopic. In the 1,3-dioxolane as shown here, in its average planar conformation, the hydrogen at C2 are homotopic. They are interchangeable by operation C2 here. On the other hand, the geminal hydrogen atoms at C4 and C5 are not interconverted by C2 symmetry operation. So you can see that these are heterotopic in turn. That is HA with respect to HB and HC with respect to HD. However, HA and HD are homotopic interchanged by the C2 axis. Also HB and HC are homotopic. As you can see here in this figure, the homotopic and the heterotopic ligands in 1,3-dioxolane is clearly represented. Allenes also has the D to D point group, and by the rotation of C2 axis, the ligands on the terminal carbons are homotopic. HA and HB are the homotopic ligands as shown here in this allene. Similarly, the orthohydrogens of the biphenyls as discussed on the previous modules under the special topic of Prostereoisomerism are homotopic because of the rotation around the C2 axis. These are also interchangeable. Phases of double bonds are similarly homotopic when they are interchanged by the operation of a symmetry axis. Now, acetone molecule with the D2H point group has two phases and are interchanged by operation of two of the three C2 axes. Two phases of acetone are homotopic as shown to you here in the figure very clearly. Now, after having studied the homotopic ligands and phases, let us now turn our attention to heterotopic ligands and phases. Two or more ligands which are identical when viewed in isolation, that is hydrogen atoms, methyl groups, fluorine substituents, etc., may nevertheless be distinct by virtue of their placement in a particular molecule. Such ligands are called heterotopic, having the Greek roots of heteros, which means different, and the topos, which means place. Just like homotopic. Homo means same but hetero means different, referring to different spatial placements of the groups in question. A trivial example relates to the hydrogen atoms at the C2 compared to those of C3 in pentane. Clearly, these two types of hydrogens in methylene group are constitutionally different. They are called constitutionally heterotopic in turn. Now I can say that with identical ligands we have stereoheterotopic and constitutionally heterotopic. The stereoheterotopic will give to enantiotopic and give rise to enantiotopic and the distereotopic ligands. So, this is the relationship profile between the heterotopic groups and isomers. The relationship between heterotopic groups and isomers show that identical ligands differentiated in the spatial arrangements are stereotopic. Stereotopic ligands and faces can be enantiotopic and distereotopic. The two criteria used to spot homotopic ligands and faces may be used to detect those which are enantiotopic or distereotopic also. Let us now thus study this criterion, that is the substitution and addition criterion for enantiotopic ligands and faces. First of all, I would like to take up the enantiotopic ligands. Those encountering the phenomenon of enantiotopic ligands for the first time are sometimes puzzled by the nature of the difference between such ligands. One way of explanation of the difference is by the very substitution criterion. That is, if replacement of two ligands in turn by a third one gives rise to different, that is enantiomeric products, then the ligands can by definition not be equivalent, that is homotopic. Ligands are heterotopic and called as enantiotopic because by the substitution of the ligands by other ligands gives a pair of enantiomers. Two ligands are enantiotopic if replacement of either one of them by a different achiral ligand give rise to enantiomeric products. I shall take an example and you shall be more clear with these concepts with this. The alpha chlorination of propanaldehyde, the molecule 20 as shown here in the figure, gives the two products 2R chloropropanol 21 and 2S chloropropanol, again 21 shown here. In other words, if we substitute the homomorphic hydrogens HA and HB by the chlorine atoms, they give two products, that is 2R chloropropanol and 2S chloropropanol, which are non-superimposable mirror images of each other, that is they are enantiomers as described in the first initial paragraph of this module. The ligands HA or HB are heterotopic or enantiotopic in nature. Now you can see here the heterotopic or enantiotopic ligands in case of propanaldehyde, that is molecule number 20 as in the figure. Having clarified this concept, let us take another example students. If we replace the hydrogen atoms of the mesotartaric acid marked by 22 by the deuterium atoms, this gives rise to enantiomers, that is mesotartaric acid, they are identical isomers. Exemplifies one of the rare instances of the molecule with heterotopic ligands but no apparent prochiral center or other element of prochirality. Now you can see here the same thing as I wanted to tell you in the figure, the heterotopic or enantiotopic ligands giving rise to the meso products. Let us take another example, the substituted allenes. If we substitute the hydrogen atoms HA and HB by deuterium atoms or different ligands which give a pair of enantiomers, we can say that ligand A, HA and HB are enantiotopic in nature. This is also shown to you here clearly in the figure. Let us now take up enantiotopic faces students. Similar criteria of addition can be established for enantiotopic faces also. Faces are enantiotopic if addition of the same reagent to either one or the other gives the enantiomers. The faces of the double bond are heterotopic and by the addition it gives enantiomers and so are called enantiotopic faces. Let us take one example regarding this. The addition of HCN to benzaldehyde by the front face and the rear face of the carbonyl, that is a double bond, gives a pair of enantiomers of cyanohydrins. The faces of the carbonyl group in benzaldehyde is enantiotopic because by the addition of HCN on two faces of the carbonyl group, it gives the same product as enantiomers. Let us take another example. The addition of the oxygen on alkene like styrene gives enantiomers of the styrene oxide as products by the attack of the oxygen on the front and the rear face of alkene. The faces of alkene and styrene are thus enantiotopic, and this is clearly shown here in the figure, and you can see the addition of oxygen on styrene. What are the symmetry criterion for enantiotopic ligands and faces? We shall now talk about that. Enantiotopic ligands and faces are not interchangeable by operation of a symmetry element of the first kind, that is Cn simple axis of symmetry, but must be interchangeable by operation of symmetry element of the second kind, that is sigma or the plane of symmetry, I center of symmetry, and Sn, that is the alternating axis of symmetry. Second, since chiral molecules cannot contain a symmetry element of the second kind, there cannot be enantiotopic ligands or faces in chiral molecules themselves. They can lead to the formation of chiral molecules although. Symmetry elements of the second kind other than sigma may generate enantiotopic ligands. That is, mesotartric acid is one of the examples, probably is one of the most stable conformation, also has a center rather than a plane of symmetry, so that its enantiotopic methane hydrogens Ha and Hb are related by the I operation. Now you can see here the inversion center created in the mesotartric acid. Enantiotopic faces are also related by a symmetry plane. For example, the plane of double bond in benzaldehyde as discussed above. The faces must not be interchangeable by operation of a symmetry axis. Here you can see the faces of benzaldehyde. So far we have discussed groups which are enantiotopic by internal comparison. Groups may also be enantiotopic by external comparison, students, that is groups in which two different molecules are enantiotopic if they are related by the reflection symmetry. Clearly, this can be so only if the two molecules themselves are enantiomeric. Corresponding groups in enantiomeric molecules are enantiotopic. For example, the methyl groups in D and L alanine, that is the amino acid. So after having talked so much on prochirality, let us just summarize this module. In this module, students, we have taught you clearly that there are three terms which have been almost used interchangeably to describe the molecules which show enantiomerism, and these are asymmetric, dissymmetric and chiral. A prochiral molecule is that which can be converted to a chiral molecule by the replacement of its one and the ligand by the other ligands or atoms, or by the addition of reagents to its faces of the double bond. We have also shown that different criteria to distinguish between homotopic and heterotopic ligands. The heterotopic ligands may be the enantiotopic or distereotopic. The homomorphic ligands or atoms of the molecules are enantiotopic. Either one of the atom replaced by the other different atom gives rise to a pair of enantiomers. These ligands are enantiotopic. In the next module, we shall discuss the distereotopicity of the molecule and their stereo descriptors for the prostereoligands and faces.